All right, today we're jumping into a bit of a chemical detective story. It's got everything: an unknown substance, a critical clue, and a big reveal at the end. So let's get right to it.
Okay, so picture this. You're in a lab and you've got this flask with a clear liquid. You know what chemical is in there, sure, but you have no clue how much of it is dissolved. What's its concentration, its strength? It's a total mystery.
And that's the big question, right? How in the world do you measure the concentration of something you literally can't see? I mean, you can't just eyeball it and say, yep, that looks like a 0.5 molar solution. No way. You've got to have a method, a reliable procedure to dig up that hidden number. Well, this is where our hero of the day swoops in. The solution to this chemical mystery is a really elegant, super precise process called titration. And trust me, it's a cornerstone of chemistry labs for a very, very good reason.
So let's look at what that actually means. The key phrase here is quantitative chemical analysis. Quantitative just means we're dealing with numbers, not just descriptions. We're not guessing, we're getting a hard number. And the whole idea is actually pretty simple. You use something you know to figure out something you don't.
And that's why it's also called volumetric analysis. I mean, it makes perfect sense, right? The whole thing is built on measuring volumes very, very precisely. So next time you hear that term, you'll know, yep, they're talking about titration. All right, let's take a look at the scene of the crime, so to speak. This is your classic titration setup. That long glass tube up top, that's called a burette. It's going to hold one of our key solutions. And down below, you've got the flask, and that's where our mystery substance is hiding. It might look simple, but don't let that fool you. This setup is incredibly powerful. So, to really get how this works, we need to meet the key players. Think of it like a little play. Each component has a super specific role to play in cracking this case. Okay, getting these roles straight is everything. First up, in the flask, we have the Analyte. That's our unknown, the chemical we're investigating. Then, up in that long tube, the Burette, we've got the Titrant. This is our standard, a solution where we know the concentration exactly. It's our main clue. And finally, we add a few drops of the indicator right into the flask with our unknown. This little guy is our informant, the secret agent that's going to tell us when the mystery is solved. The entire experiment, all this careful setup, it all builds to one single critical moment, a tipping point where everything is perfectly balanced. And the answer is right there, just waiting to be revealed. Now, this is a really important distinction. In a perfect world, we're aiming for something called the equivalence point. This is the theoretical moment when the amount of stuff we've added is chemically identical to the amount of stuff we started with. The problem? It's completely invisible. You can't see it happen. So what we look for instead is the endpoint. And that's the moment our informant, the indicator, physically changes color. That's our signal that it's time to stop. Yeah, ideally the endpoint and the equivalence point would happen at the exact same time. But in the real world, there's always a tiny, tiny gap between the theoretical perfect moment and the moment we actually see the color change. That little difference is called the titration error, and the goal of any good chemist is to make that error as tiny as humanly possible. And boom, there it is, the big climax. Sometimes it literally comes down to a single drop. 1 second it's one color, the next it's completely different. That right there, that's the endpoint. That's our informant basically yelling, "Stop, we're done." And what's really cool is that there isn't just one informant. Scientists have a whole palette of them to choose from. These different indicators change color at different pH levels, so you can pick the absolute perfect one for whatever mystery you're trying to solve. It's kind of like having a whole squad of specialized detectives, each good at a different kind of case. Okay, so our informant has done its job. We've seen the color change, we've stopped adding the titrant, and we've carefully written down exactly how much we used. Now comes the best part, cracking the code and finding the answer. The math behind this actually rests on one really simple, beautiful idea. At that perfect equivalence point, the amount of the known stuff we added is chemically equal to the amount of the unknown stuff we started with. Or to put it even more simply, the moles of the titrant equal the moles of the analyte. That's it. That simple equation is the key that unlocks this entire mystery. All that careful work with the glassware, it was all to get us to a point where we can confidently say this is true. So how do we use that? Well, in chemistry, moles can be calculated by multiplying molarity times volume.
So our simple statement moles equals moles turns into this really useful formula. Think about it. We know the molarity of our titrant, and we just measured its volume. We also know the starting volume of our analyte in the flask. The only thing we don't know is the molarity of the analyte, our mystery number. A little bit of algebra, and boom, case closed.
So we've cracked one case, but the amazing thing about titration is that it is not a one-trick pony. This same basic technique can be tweaked to solve a whole bunch of different chemical mysteries. I mean, look at the versatility here. You can use it for your classic acid-base neutralizations, for reactions that create a solid, for complex metal reactions, and even for redox reactions where electrons are flying around. It's like the Swiss Army knife of quantitative chemistry.
And that kind of brings us to a final interesting thought. You know, we live in this world of super complex, high-tech, automated machines that can analyze anything. And yet, this simple manual technique, which really just relies on careful measurement and a good eye, is still absolutely essential. It kind of makes you wonder, right? In a world of complexity, why is something so simple but so precise still so incredibly powerful?